Hey kiddos, happy asynchronous class. This is for Thursday, September 24th. And today we're going to talk about doing calculations with resistors in complex circuits. So we'll be looking at a circuit where resistors maybe don't have all the same value. Okay, all of our light bulbs in the light bulb lab all had the same value for the resistance. Or what if two resistors are in parallel and one is in series? So that's what we'll be looking at today. And then in our live class next Monday, we will look at some pretty crazy situations in which maybe there are multiple power supplies. All right, so as a reminder, today your light bulb labs are due. Please click that button to submit those. And if you have any questions about the problems that I assigned last class or the problems that I assigned today, I'll be around in our class meet and you can please feel free to come ask me a question. All right, let's get moving. All right, so let us first just consider situations in which the resistors have different values. Okay, so what is a resistor? We talked about that last class. A resistor is just an object that is placed in a circuit that can provide a potential drop. You can think of it as electrical friction. It takes some energy out of the electrons and produces heat, light, or some sort of useful motion. Okay, and I think I can show you one here. Okay, so I found a resistor. It's a little tiny device on a wire. And if I bring it closer to my camera, let's see right there. I don't know if it'll focus on it, but it's just a little tiny nub. And those stripes, there's a special code that you can use to determine the resistance of that resistor using the stripes code. And we can go over that at some point as well. Okay, but it's just a tiny little guy. All right. The symbol for a resistor is typically just a squiggle, like you're seeing here. But sometimes you might, instead of seeing a squiggle, oh, it's purple, you might just see a box connected in the circuit. It kind of looks like one of those resistors. Okay, so those are two common symbols for resistors. All right, so let's take a look at the circuit on the left. I took a screen grab from our Cutnell and Johnson textbook, and it's not looking great, but it is what it is. All right, so what we've got here, I'm going to get rid of my face, is we've got a battery that has a voltage of 24 volts. So the voltage here, this is 24 volts. And down here in the negative end is 0 volts. All right, the resistors, R1 is 50 ohms, R2 is 25 ohms, and R3 is 10 ohms. All right, so let's find the value of the total resistance and the total current. All right, so in series, the total resistance is just the sum of all of the resistances. So 50 plus 25 plus 10 is equal to 85 ohms. All right, and then if we apply Ohm's law, we could say V equals I R, right, with the subscript total, to figure out what the total current is through each resistor. Okay, so we could then write this, if we wanted to solve for current, the total current is the total voltage over the total resistance, which is 24 over 85. All right, so the total current is 0.28 amps. All right, so I can draw that. Conventional current goes from positive to negative. So the total current is 0.28 amps. All right, now this is a series circuit. So all of these resistors are experiencing the same amount of current, right? So 0.28 amps is the current going through resistor 1. And it's the current going through resistor 2. And it's the current going through resistor 3. Okay, and if we know that, if we now know the resistance of each resistor, and we know the current going through each resistor, we can find the potential drop or the voltage across each resistor. Okay, so we could then say, right, voltage 1 equals current 1 times resistance 1. Current is 0.28 times 50. And what we get for the voltage across resistor 1 is, all right, the voltage across resistor 1 is 14 volts. And I went through the same process with resistors 2 and 3, multiplying the current running through resistor 2 times the resistance of 25. So we get a potential drop of 7 volts provided by resistor 2, and then a potential drop of 2.8 volts provided by resistor 3. Okay, now here's the thing. Remember, if we're starting at 24 volts, each of these resistors is supposed to provide a potential drop until we get back down to the 0 volt side of the power supply. There should have been 24 volts of potential drop provided by those 3 resistors. So let's check that out. So we start out with 24 volts, right? We lose 14, 7, and 2.8 volts. So if we add those 3 potential drops together, we end up with 23.8 volts of potential drop provided by the resistors. Now, we're going to go ahead and say that that's good enough for government work. Okay, so that's pretty close within rounding, because you could argue that all of the other voltages were rounded to the nearest whole volt. So we could say this is 3 volts of potential drop, and then we've got our full 24 volts, okay, of potential drop. All right, I'm gonna zoom in over here, and I'm going to erase some of this to take a look at our parallel circuit. All right, so I've gone ahead and filled in the values for the resistances. We've got our same 3 resistors in parallel now, and we can visually see that they're in parallel. Sometimes we don't see these junctions all joining at the same spot, but these are considered in parallel. Okay, so another way I would have drawn this probably like right? Like so. That's how I would have drawn it. But I'm not the textbook author, so we will just leave it at that. Okay, so we've got the same 24 volts across the power supply, 3 resistors connected in parallel. We want to figure out what is the total resistance of the circuit, and that'll help us find the total current. Okay, and then once we know the total current, we can figure out what the current is through each of these resistors and what the potential drop is across each of the resistors. All right, so to find the total resistance, right down here, total resistance in parallel, remember, is the sum of the inverse of the individual, R2, R3, right? And then you take the inverse of those. Okay, so we've got 1 over 50 plus 1 over 25 plus 1 over 10. Take the inverse of that, and you should get a total resistance of 6.25 ohms. Okay, that's the total resistance. And so if we then apply V equals IR, V total equals I total times R total, we can get the total current is equal to the total voltage across the power supply, which is 24 volts over 6.25. And we get a current of 3.84 amps. All right. So let's say current is going to be red. Okay, so we'll say I total is 3.84 amps. Okay. All right. Now, when we're working with parallel circuits, it's oftentimes prudent to find the potential drop across each resistor first. And that's because, remember, the potential drop across each resistor in parallel is the same, right? Right here, we've got our high voltage of 24 volts. Right here, we've got our low voltage of 0 volts. All right, so what that means is that no matter what path the current, the electrons take, they will have to have, the resistor is going to have to provide a potential drop of 24 volts, right? So if the current goes through resistor 1, right, we'll call that current 1, right? It will go from 24 volts down to 0 volts. And so that means the potential drop across resistor 1 is 24 volts. Okay. If a current goes through resistor 2, same thing. It would meet back up over here, and those electrons would need to have gone through the same potential drop. Okay. So all 3 currents, right, through each resistor, right, they're going to go from 24 volts to 0 volts because they're going to only go through one resistor, and they will have no other thing to provide that full potential drop they need. Okay, so we've got currents 1, 2, and 3. Those will be different, but the voltages will be the same.